In this video, we're going to focus on synthesis reactions, reactions associated with alkynes, Grignard reagents, and we're going to cover some other examples. But let's begin. So this is acetylene, which is basically a 2-carbon alkyne. And what we're going to do first is we're going to add sodium amide to it, NaNH2. The NH2 ion is a very strong base. It's strong enough to remove the hydrogen from the alkyne. The pK of an alkyne is relatively acidic. It's about 25 compared to most carbon-hydrogen bonds. So once we remove the hydrogen, we now have what is known as an acetylide ion. And whenever carbon has a negative charge, it's relatively nucleophilic. And so we can react it with an alkyl halide. Because bromine is more electronegative than carbon, it pulls the electrons toward itself. And so bromine has a partial negative charge, and therefore carbon has a partial positive charge. When you have a positively charged carbon atom and another one that's negatively charged, these two carbon atoms will connect and they will create a carbon-carbon bond. So this carbon with a negative charge is attracted to the carbon with a positive charge. And so the two will connect. And that's how we can make carbon-carbon bonds. And so this is the product for this reaction. So I just want to give you an overview of the mechanism of that reaction. But now let's say if you have this alkyne, what reagents do you need to make this product? How would you propose a list of reagents that you need to make that? And feel free to write the mechanism as well. Now, notice that we have 2 carbons already. But right now we have on the right side 6. So we need to add 4 carbons. So basically we need to add this part of the molecule. So what we need first is we need sodium amide to remove the hydrogen. And then second, we need an alkyl halide, basically a 4-carbon alkyl halide. And then third, we need to reduce the alkyne into an alkene. And what we could use to do that is we could use a sodium metal with liquid ammonia. So now let's go over the mechanism for this process. So in the first step, the amide ion is going to remove a hydrogen, generating the acetylide ion. And then in the next step, this is going to react with, let me redraw that better. This is going to react with 1-bromobutane. So this is the carbon that has the partial positive charge. It's the carbon that is directly attached to the bromine atom. And so the acetylide ion is going to attack the carbon and it's going to expel the bromine atom. And it does so by means of an SN2 reaction. And so at this point, we have a total of 6 carbon atoms. Now once we add sodium metal with liquid ammonia, this is going to reduce the triple bond or the alkyne into an alkene. And so that's how we get this product. So let's try another example. Let's say if you have this alkyne, and so starting from acetylene, you want to make this product. How would you do it? So notice that the 2 carbons of the triple bond are basically these 2 carbons with the double bond. So we need to add an R group for the left side and for the right side, which we can do because there's 2 hydrogens, and we can remove both of them. So first, let's add these 2 carbons. Step 1, we need to add sodium amide to remove the hydrogen. Step 2, we're going to add 2 carbons and a Br, so basically a 2-carbon alkyl halide, or in this case, ethyl bromide. Now, step 3, we need to use sodium amide again to remove the second hydrogen. And then in step 4, we're going to add this part of the molecule. So basically, just redraw what you see. We need a total of 5 extra carbons. And then we're going to add a leaving group to it. Now, how can we convert a triple bond into a cis double bond or a cis alkene? To convert the alkyne into a cis alkene, you need to use hydrogen gas, but with the Lindlar's catalyst. The Lindlar's catalyst is basically a deactivated palladium catalyst. So you might see it as a palladium poison with like barium sulfate or something, or with some other ionic compound. So it's just a modified or deactivated palladium catalyst, and it's going to give you the cis alkene. Another way in which we can make a carbon-carbon bond is by using a Grignard reagent. So here's an example of a Grignard reagent. What we have here is methyl magnesium bromide, and we know oxygen has a partial negative charge. It's more electronegative than carbon, but the carbon that is attached to the oxygen has a partial positive charge. Now the CH3 that's attached to the metal, to magnesium, that carbon has a partial negative charge. So whenever you have a nucleophilic carbon and an electrophilic carbon, those two will react to create a carbon-carbon bond. And so initially, we're going to get this alkoxide ion, and we're going to add a CH3 to it. Now, the magnesium and the bromide, they're ionically bonded to the oxygen with a negative charge. Now, once we acidify the solution using H3O+, we can now protonate the alkoxide ion, and so we're going to get a tertiary alcohol. So that's the Grignard reagent. And in your organic chemistry course, you might see a few examples dealing with this reaction. So, starting with cyclopentanone, how can you make this product? What reagents do you need? Now, you can use a Grignard reagent or an organolithium reagent, but let's use a Grignard reagent. So, we need to add 4 carbons to this compound. So basically, we need 4 carbons and an MgBr group. In the second step, we need H3O+. That's it. That's all the reagents you need to make that product. Now, whenever you add a Grignard reagent to an aldehyde or a ketone, only one R group will be added. But let's say if you have like an acid chloride or an ester, you can add 2 R groups. So for example, let's say if you were to use methyl magnesium bromide followed by H3O+. This will be reduced to an alcohol, but by the addition of 2 methyl groups. So let's see why that's the case. So starting with this acid chloride, the Grignard reagent is going to attack the carbon-no-carbon. And so we're going to add a CH3 to it. And then when that happens, this oxygen is going to regenerate the double bond, or the pi bond, and it's going to expel the chlorine atom. The chlorine is a good leaving group, so it's very easy to kick it out. And so right now we have a ketone. Now at this point, the Grignard can still react with a ketone. So another Grignard reagent that's in a solution will continue in its reaction. It's going to reduce the ketone as well. So now we have an oxygen with a negative charge. And at this point, we have 2 methyl groups. So the reaction stops until we acidify the solution with hydronium ions. So in the end, we're going to get a tertiary alcohol. So the Grignard reagent is very useful for making alcohols. And it does so by adding carbon atoms. So this is the answer for this reaction or example. So starting from an acid chloride or even an ester, how can we convert the acid chloride into a ketone? We know that a Grignard reagent won't stop at the ketone level. It's going to take it all the way to an alcohol. But what if we wanted to stop at the ketone level? Or what if we want to take an ester and convert it into the aldehyde level? How can we do that? Well, if you want to make a ketone, what you need to use is the Gilman reagent or the organolithium, organocopper lithium reagent. This will reduce the acid chloride to a ketone, but it won't react with the ketone. And if you want to get the aldehyde, you need to use something called DIBAH. So I'm going to go over the mechanism for these processes. So starting with the acid chloride. Here's the Gilman reagent. There's two methyl groups attached to the copper atom, and there's a lithium ion that's next to it. So one of the methyl groups attacks the acid chloride, but not both, just one. And at this point, one of the lone pairs will be used to regenerate the pi bond, expelling the chloride leaving group, and the reaction stops here. Only one of the methyl groups is nucleophilic. Once you get rid of the methyl group, the copper will lose this negative formal charge, and so it's going to be strongly attached to the remaining methyl group. So only one of the methyl groups is nucleophilic. But what you need to keep in mind is for the Gilman reagent, if you combine it with an acid chloride or an ester, it's going to stop at the ketone level. And that's what you want to take from this reaction. So now let's go over the mechanism between an ester and DIBAH. So DIBAH, it's basically an aluminum atom that has only one hydrogen atom, but also has like 3 OR groups. Now the aluminum atom has a negative formal charge and lithium has a positive charge. So whenever hydrogen is attached to a metal, it's going to have a partial negative charge. It's nucleophilic, kind of like when a carbon is attached to a metal. Keep in mind, formal charge and partial charge are not the same thing, they're different. Now this hydride is going to attack the carbon, and then the pi bond is going to break. And just like before, the carbonyl group is going to be regenerated by the expulsion of this leaving group. Now the OCH3 is not a great leaving group, but it can still leave. And so the end result of this reaction is an aldehyde. It stops at this level. So let's say if you have an acid chloride and you want to make this particular product. How would you go about doing it? So feel free to pause the video and see if you can find the right reagents to make this product. Now, what you want to focus on, you want to think about what you need to add to make this product. So before, notice that you have a chlorine and it left. But notice the groups that are attached to this carbon atom. Let's focus on that carbon. So these 3 carbons were already there. We didn't add it. We added a benzene ring, but notice that there is an invisible hydrogen that is now visible since I wrote it there. So basically we added a hydrogen and a benzene ring. Now, we can't add a Grignard reagent right now to this acid chloride because it's going to add 2 R groups. Basically 2 R groups that contain carbon. So we want to add a hydrogen, so we don't want to use the Grignard right now. So the first thing you want to do to add the hydrogen is you want to use DIBAH. It's going to take it down to the aldehyde level by adding a hydrogen. And now, you don't want to use the Gilman reagent at this point. It doesn't really react with ketones, and I haven't seen it react with aldehydes, but what you want to use now is the Grignard reagent. Or you can use an organolithium reagent So you can use CH3 MgBr at this point. Well, not CH3, but we need to add the benzene ring. So you can use phenyl magnesium bromide followed by H3O+. That's the Grignard reagent. Or you can use this reagent, an organolithium reagent with a benzene ring. So both of these can work. So, and that's going to be the answer. So step 1 really is using DIBAH to add the hydrogen. Once you do that, step 2 is to add phenyl magnesium bromide, and then step 3, H3O+. And that's how you can make it. So now let's say if we have an ester. And what reagents do we need to make this particular product? How would you make it? So we need to add 2 different R groups. And how would you make this one as well? So I want to highlight the difference here. Notice that for the product on the bottom, we're adding the same R groups. So if you want to add 2 of the same type of R groups, simply use a Grignard reagent. So the reagent that we need is basically this Grignard reagent followed by H3O+. Now, in the first example on top, we want to add 2 different R groups. So you don't want to use a Grignard reagent initially. You want to do something else. What you want to use is the organolithium copper reagent. So let's use CH3 CH2 times 2 copper lithium. What's going to happen is it's going to take it down to the ketone level. It's going to replace the OCH3 with one of these R groups. So initially you're going to get this product. So now that it's at the ketone level, you can now add the Grignard reagent to add the second R group. So we're going to use phenyl magnesium bromide. And that's going to add the second R group, which is different from the first. And then step 3, we're going to add H3O+. So that's what you can do if you wish to add 2 different R groups to an ester or an acid chloride. So first use the Gilman reagent for the first R group, and then use a Grignard reagent for the second R group, and then you can get it done. Now, if you want to add 2 R groups that are identical to each other, you can simply use the Grignard reagent, and you can just write 2 equivalents of that reagent to get this product if you want to get it in good yield. Now let's talk about how some of these reagents are made. Starting with an alkyl halide, all you need to do to make a Grignard reagent is simply add a metal to it, particularly magnesium metal. Magnesium is going to insert itself between the carbon and the bromine atom. So basically, you could see it this way. This pretty much helps. Magnesium has 2 valence electrons, and it's going to give the carbon atom those valence electrons. Right now, carbon is partially positive. It's directly attached to an electronegative atom. And so once magnesium gives those 2 electrons to carbon, carbon has no need of being attached to bromine. So right now we have a carbon that has a negative charge, and since magnesium lost 2 electrons, it has a +2 charge, and bromide, it pulled those 2 electrons in this bond, so it has an extra lone pair, so it has a negative charge. So now we can combine. Imagine if this carbon with the negative charge attacked the Mg. What we would have is something that looks like this. The magnesium will now have a +1 charge. If you add -1 and +2, you get +1. Now imagine if the bromide ion attacks the magnesium. So a plus and a minus, they pretty much will neutralize each other, and so you get this compound. So that's just one way to see how this works. It may not be the exact mechanism, but it helps you to understand how these atoms are like bonded to each other. Now, what about making the organolithium reagent? Now, what you need is 2 equivalents of lithium, because lithium has only 1 valence electron, whereas magnesium has 2. And to get rid of that bromine, you need 2 electrons. So I'm going to draw 2 lithium atoms, each with 1 valence electron. So this lithium is going to contribute 1 electron, and this one is going to contribute the other electron. And so bromine is going to leave. Whenever you have a half arrow, it represents the flow of 1 electron. A full arrow represents a flow of 2 electrons. And so now we have a carbon atom with a negative charge. We have 2 lithium ions, and we also have a bromide ion. So this carbon with a negative charge can pair up with the lithium. And so when you add a negative and a positive, the net charge is 0. So this is going to be the organolithium reagent. So notice that there's only 1 lithium atom attached to it, but no bromine atom. Now, these 2 can get together and form an ionic bond. And so these are the products of this reaction. So this reagent, I'm going to represent it as RLi. Now, if you take this organolithium reagent, pretty much if you have like 2 of them, you can react it with copper chloride, copper 1 chloride specifically, which I'm going to write it like this. So, one of the R groups will attack the copper, kicking out the Cl. So now you have RCu, and the lithium has a +1 charge, and chloride has a -1 charge. So these 2 will get together and form LiCl. Now, the second R lithium compound will also attack the copper. Now, keep in mind though, the R group has a negative charge, lithium has a plus charge. So if we add this extra R group, we're adding basically a negative charge to this compound. Right now the compound has a net charge of 0. But once we add this -1 charge to it, it's going to have an overall charge of -1. So now that copper has 2 R groups, it has a formal charge of -1. And so it's going to pair up with the lithium. And so thus we can write it as R2 copper lithium. So when you take an organolithium reagent, you need 2 equivalents, and when you react it with like copper chloride, you're going to get R2 copper lithium plus LiCl. So that's how you can make the Gilman reagent. So let's say if you have an alkyl halide, the first thing you could do is add lithium to it, and this is going to turn into this compound. And then once you add copper chloride, assuming you add enough of this, let's say 2 equivalents, then you can get the R2 copper lithium reagent. Now, what can we do with this? We can react this group with another alkyl halide. Notice what's going to happen. So if we start with 1 bromobutane, and if we react it with an organocopper lithium reagent, this R group will attack this carbon and expel the Br. So basically we can couple 2 different alkyl groups together. So here we had 4 carbons, and here we also have 4 carbons, so we're going to get an 8 carbon structure. So that's how you can combine 2 alkyl groups together. So let's say if we have a 5 carbon alkyl halide and a 4 carbon alkyl halide. So step 1, if we add lithium to one of these alkyl halides, and then step 2, if we add a copper chloride to it, and step 3, if we add this thing, we can connect these two together. And so we're going to get 9 carbons. And so basically we're just combining these two chains together. So that's how you can combine two alkyl halides. So let's say if we have the following alkyl halide. What reagents do you need to make this product? How would you do it? So let's count the carbons that we already have. 1, 2, 3, 4, 5. I'm counting the longest chain. We also have 2 additional methyl groups in carbon 2. So if I count the same carbon atoms, 1, 2, 3, 4, 5, I know that this structure is already present in my reactant. So what I need to add to it is the part that remains, which is this part. So step 1, I'm going to convert this alkyl halide into an organolithium reagent. So step 1, I'm going to add lithium, and then I'm going to convert it into a Gilman reagent. So I'm going to add a copper chloride. And then in step 3, once I have my Gilman reagent, I'm going to add the other alkyl halide that I need, which is basically this one. So I need an alkyl halide that has a bromine on this carbon. So I'm going to draw it backwards. So I'm going to start with this, the 2 methyl groups at the end, basically like an isopropyl group. So let me count the carbons. 1, 2, 3, 4, 5. So on the 5th carbon, I need a bromine atom. So 1, 2, 3, 4, 5, and then Br. So those are the reagents I need to make this particular product. But let's go through each of the steps. So step 1 was the addition of lithium, which will make the organolithium reagent. And then step 2 was adding copper chloride. Now granted, I need to use 2 equivalents. So let's say if I have 8 moles of this product, all I need is 4 moles of copper chloride. So I need like a 2-to-1 ratio, so to speak. And so I'm going to have 2 of these R groups, and then copper lithium attached to it. So now I can react it with the other alkyl halide that I had. And so what's going to happen is one of the R groups is going to attack this carbon and expel the Br. And then so the product that I'm going to get looks like this. And so this will be my answer. I believe I counted the carbons correctly, but let me make sure. Yeah, this should be right. And so that's how you can combine 2 alkyl halides together, if you ever need to do so. Now, there's some other cool things that you can do with organolithium reagents. So let's say if you have an alkene, and attached to this alkene is like a halogen on it. You can add an organocopper lithium reagent to it. And what's going to happen, the net result is that you're going to replace the bromine atom with a methyl group. And the double bond is still going to be there. So here's how it works. So one of the methyl groups is going to attack the carbon that has the bromine atom. Because keep in mind, that carbon has a significant amount of partial positive charge. But it's not like an SN2 reaction where it attacks the carbon and expels the bromine atom at the same time. So this doesn't happen because it doesn't approach the molecule from the back. So, or at least not directly from the back. So it's not easy. That doesn't happen. So what happens instead is as the methyl group attacks the carbon, the pi bond breaks. So it's not really like an SN2 reaction, but the overall effect is a substitution process. So the bromine atom is still here initially at this point, and the methyl group has been added. So the first step was an addition step, and then the second step is going to be an elimination step. The carbon with the negative charge is going to use the lone pair to regenerate the double bond, and it is at that point that it's going to expel the bromine atom. And so the second step is an elimination step. So this is called like an addition-elimination reaction, which combined overall is still considered a substitution reaction, because in the end we replace or substituted a bromine atom with a methyl group. So once that lone pair forms a double bond and a bromine atom is expelled, now we're going to have the product, which looks like this. So the Gilman reagent is very useful for replacing halogens with R groups. Now, you can also do something similar with a benzene ring. So if you were to add a Gilman reagent to this, you can replace the bromine atom with a methyl group. So this can work as well. And the mechanism is very similar to the last example. So starting from an alkane, how can you make an alkene? And also, how can you make an alkyne? And from an alkane, how can you make a secondary alcohol and also a primary alcohol? And how can you make an aldehyde and a ketone? And how can you get, let's say, an amine as well as a carboxylic acid, or even an ester? Or what about an ether? So we're going to talk about how to get these different functional groups starting from an alkane. So let's begin. Right now, with an alkane, you can't really do much. So the only thing you can do is probably add a bromine atom to it, and that's usually the first thing you should do. And one of the best ways to do it is to add NBS. Now you may have to add like heat or light or some sort of radical initiator. But once you add NBS, it's going to replace the most substituted hydrogen with a bromine atom. So in this case, bromine is selective. It's going to replace the secondary hydrogen faster than it would replace the primary hydrogen. So if you had a primary, secondary, or tertiary hydrogen, the bromine atom will selectively replace the tertiary hydrogen. So more than 99% of the product will be in this form. You might get a small amount of 1-bromobutane, but for the most part, more than 99% is basically going to be like 2-bromobutane. So you get this product in a very high yield. Now once we have 2-bromobutane, we can add sodium hydroxide, which is going to be an E2 elimination reaction. And in this reaction, the hydroxide ion is going to grab a hydrogen, form a double bond, and expel the leaving group. So that's how we can make the alkene. And once you have the alkene, you can do a lot of things. So with the alkene, you can easily make a secondary alcohol or even a primary alcohol. Now, to make the secondary alcohol, the reagents that you can use is mercury acetate with H2O followed by sodium borohydride. This is the oxymercuration demercuration reaction, and it proceeds with Markov-Addition. Now, if you want to make the primary alcohol, you can use BH3 borane with THF, followed by hydrogen peroxide and hydroxide. So this will give you the anti-Markovnikov product. So this is the hydroboration oxidation reaction. Now, if you were to add a PCC, the alcohol will be oxidized into a ketone. And if you add PCC to the primary alcohol, it's going to be oxidized into an aldehyde. Now, if you were to use a strong oxidizing agent to this primary alcohol, like chromic acid or potassium permanganate with H3O+, you can convert it into a carboxylic acid. Now, once you have the carboxylic acid, you can do a lot of things. So starting from the carboxylic acid, you can add SOCl2 and convert it into an acid chloride. And once you have the acid chloride, you can react it with, let's say, ammonia, and that's going to turn into an amide, with HCl being a byproduct. You can also add an alcohol. If you add an alcohol, HCl will be removed and you're going to get an ester. So basically, you're going to replace the chlorine with this part of the molecule. And so an acid chloride plus an alcohol will give you an ester. And let's say if you were to add a carboxylic acid to it, the chloride will be replaced with this part of the molecule. Basically, you just have to get rid of the hydrogen and the chlorine. So HCl is going to be the byproduct. So this will give you an anhydride. Now, starting back with the ketone and the aldehyde that we had in the previous examples. Once you have the ketone, you can add like ammonia to it. And you're going to get an imine, which looks like this. If you add ammonia to this aldehyde, you will also get an imine, but it's going to be on the primary carbon instead. Now, you can reduce the imine with cyanoborohydride, so sodium cyanoborohydride, or NaBH3CN. If you use it on the secondary amine, the double bond is going to be reduced to a single bond, so you're going to get a primary amine. So that's going to be the product for this reaction. And for this one, the amine is going to be on the primary carbon as opposed to the secondary carbon. So here it's on a secondary carbon, but this is still considered a primary amine because the nitrogen only has, or is only attached to one carbon. So this is a primary amine, but it's on a primary carbon. So as you can see, you can get both types of amines by reason of that reaction. Now, going back to the alkene, we can make an ether if we use the alkoxy mercuration demercuration reaction. So if we were to use water, we're going to get an alcohol. But if we use an alcohol instead, like CH3OH instead of water, instead of getting an OH group, we're going to get an OCH3 group on the more substituted carbons. That's how you can convert an alkene into an ether. And you know how to convert the alkane into an alkene. Now, to get like a primary ether, or an ether on the primary carbon, once you have this alkene, you can add HBr with peroxide, H2O2. And so this is going to put the bromine atom on the less substituted carbon. This reaction proceeds with anti-Markovnikov addition. And now you can add sodium methoxide. When you use methoxide with a primary alkyl halide, the predominant mechanism is the SN2 reaction. And so the methoxide is going to attack the carbon from the back, expelling the bromine atom. And so you're going to get an ether on a primary carbon as opposed to the secondary carbon. So now, starting with the alkene, how can we convert it into an alkyne? How would you do that? So the first thing you need to do is you need to add Br2. So this reaction is going to put 2 bromine atoms across the double bond. And then at this point, you can use a strong base, but we're going to use sodium amide. So the NH2 minus ion is a very powerful base, and the first thing it's going to do is it's going to grab one of the hydrogens, and then a double bond is going to be formed, and one of the Br is going to leave. So this is going to be an E2 reaction. So right now we have a double bond with 1 bromine atom still on it. So now another NH2 minus ion is going to remove this hydrogen. It's going to form a triple bond and expel this Br. So that's how we're going to get the alkyne. That's how you can make it. Now, starting from the alkyne, how can we make a ketone and an aldehyde from it? There's some reagents that you should know regarding this. So to make the ketone, what you really need is mercury sulfate with water and sulfuric acid. Now initially, before you get the ketone, you're going to get something called an enol. And the enol is going to tautomerize into the ketone. Now for the next one, if you want to make the aldehyde, you need to use a reaction that's similar to hydroboration. But notice that there's only 1 hydrogen on the boron, it's not 3. Otherwise you'll get some interesting side products. But other than that, it's very similar to the hydroboration oxidation reaction. Now initially, you're going to get an enol that looks like this. And it's going to tautomerize into the aldehyde form. So the enol is the intermediate of these reactions, but this reagent will generate the ketone for the most part, and this will produce the aldehyde if you have a terminal alkyne. That's an alkyne at the end of the chain. Now, starting with a ketone, how can you convert a ketone into an alkene? How can you make this product? If you want to convert a ketone into an alkene, the best way to do it is to use the Wittig reaction. So you need to add this part to the Halide. So it's going to look like this. And so that's what you need. So with that in mind, try this example. Starting from this ketone, find out the Halide that you need to make this product. So all you need to do is draw the Halide and then add this portion of it to it. And just draw exactly what you see. So that's how you can convert a ketone into an alkene, and you can make all sorts of alkane using the Wittig reaction. So here's a question for you. How can you turn butane and ethane, how can you combine them to make cyclohexane? So if you have butane and ethane and you have some other reagents, what reagents can you use to make it form a ring? So feel free to pause the video, think about it, see if you can solve it, and then when you're ready, unpause the video to see if you can, if you have the right answer. Now there might be more than one way of getting this done, but here's one way to do it. So let's start with, first let's clear the page. Let's start with butane. What we're going to do first is add NBS. And so we're going to replace a secondary hydrogen with a bromine atom. After that, we're going to add sodium hydroxide. So this is going to be an E2 elimination reaction, and the hydroxide is going to get rid of one of the hydrogens. Actually, I don't want to use hydroxide. I take it back. Because it's going to give me the zeta product. I want the Hoffman product. So I'm going to use a bulky base. Terbutoxide. So terbutoxide is going to go for the more accessible hydrogen. That is the primary hydrogen and not the secondary one. So we're going to get a terminal alkene, which is what I want. So now that we have this terminal alkene, what I'm going to do is use NBS again. And it's going to replace the allylic hydrogen. Now at this point, I can use any strong base, terbutoxide or hydroxide, because hydroxide will easily remove this hydrogen, so we can get a conjugated alkene. So it's going to grab this hydrogen, form a double bond, and expel the bromine atom. So now what I have is 1,3-butadiene. Now I'm not sure if you see where I'm going with this, but in time you will. Now starting with ethane, I'm going to use NBS again to get ethyl bromide. And then I'm going to use sodium hydroxide, which is going to be an E2 reaction. And that's going to give me an alkene, particularly ethene. So now what I'm going to do is I'm going to combine these two together. So I have 1,3-butadiene and ethene. What do you think is going to happen when you put these two together? 1,3-butadiene is a diene that is going to participate in the Diels-Alder reaction. The Diels-Alder reaction is a 4+2 cycloaddition reaction. And so it's going to form a 6-membered ring, which is going to look like this. So one of the double bonds, particularly this one, connects carbons 1 and 6 together. So the pi electrons in that bond is used to make this sigma bond, and the double bond between 3 and 4, those pi electrons are used to connect carbon 4 and 5. So there's only one double bond that's left over. Now, since we wanted cyclohexane, not cyclohexene, what we could do is add H2 with a palladium catalyst, and it's going to convert the alkene into an alkane. So that's how you can make cyclohexane from butane and from ethane. So now, from cyclohexane, how can you make benzene? This is going to be the last example for this video. So what do you think we need to do? Well, the first thing we need to do is add NBS. So we're going to add a bromine atom, or replace a hydrogen with a bromine atom in this ring. And then once we do that, we're going to add sodium hydroxide. So the hydroxide is going to get rid of the bromine atom, and it's going to form a double bond. And we're going to repeat this process multiple times. But right now, what we have is cyclohexene. So starting from cyclohexene, we're going to add NBS again. And NBS this time is going to replace the allylic hydrogen, the hydrogen that's one carbon away from the double bond. And so we're going to get this. And then we're going to add hydroxide again. So at this point, hydroxide is going to get rid of this hydrogen, form a double bond, and expel the bromine atom. So now we have two double bonds. And so we're going to add NBS again. And one of the allylic hydrogens will be replaced. It really doesn't matter which one, because at this point the two remaining hydrogens are both allylic. So we're just going to replace one of them with a bromine atom. And then hydroxide is going to remove the other hydrogen, form a double bond, kicking out the Br. So the driving force for this reaction is stability. Every time you add a new double bond, it becomes more stable compared to the previous double bond. So right now we have 3 double bonds, so it's very stable. So benzene, the double bonds in the benzene ring are more stable than the double bonds in 1,3-cyclohexadiene. And these 2 double bonds, they're still conjugated, so they're more stable than cyclohexene. So this reaction can easily work because the driving force is stability. We're going from a less stable compound to a more stable compound. And when that happens, it's easy to form that kind of product. So that is it for this video. So you have some examples on how to synthesize different compounds. Of course, there are many other reactions out there. If you want more reactions, do a YouTube search and check out my video on Organic Chemistry 1 and 2 reactions review study guide. It has like a list of reactions and reagents that will help you for Organic 1 and 2. So check that out when you get a chance, and thanks for watching this video and have a great day.